Pseudonautics, the study of fake space exploration.
Episode 3 Soft Landing. In Episode 1, we noticed some strange reflective things in the Apollo 17 sky. In Episode 2, we saw that NASA is still actively and suspiciously altering the Apollo photographic record. In this episode, we'll address one of the most important arguments against the authenticity of the Apollo pictures, the feeble effect of the lunar module descent engine on the soil. Here's the Apollo 14 allegedly sitting on the moon. The effects of the descent engine on the underlying soil seem to be discreet, to say the least. Here is official NASA artwork depicting a lunar landing. Quite a blast that seems to have left a noticeable crater. Such a crater is also present on the very official Apollo 13 Lunar Module 7 insignia. Apparently, NASA artists and technical illustrators got the ridiculous idea that the lunar module descent rocket would make a hole in the soft lunar soil. What does the semi-official debunking site Clavius.org say about this? Quoting, "I have yet to see a conspiracist who has given any kind of quantifiable justification for this belief." According to Clavius.org, this picture shows unmistakable signs of the descent engine having worked on the lunar surface. Unmistakable indeed. I'll concede that we have what appears to be faint radial lines. This one, also featured on Clavius, is even supposed to show signs of reddening due to the propellant oxidizer nitrogen tetroxide. I've dug up this picture, which shows a sizable large crater. Is this the long south descent engine crater? No. It is not under the nozzle and it lacks radial lines. It gets much more convincing if we alter the picture to put the crater under the lunar module. This is the kind of hole people expect to see. Here's some well-known 29 kN rocket footage. Imagine this rocket pointed to the ground. As the lunar module descends, I expect the powerful exhaust to dig a sizable hole. But physics can be misleading and our expectations can be wrong. One often heard allegation is that the descent engine was cut off well above the surface. This descent footage from Apollo 14 clearly shows that the engine was cut well after contact. We start seeing dust while the astronaut announces an altitude of 150 feet. Thus the jet already affects the lunar surface from 45 meters. At a speed of 3 feet per second, the lunar module descends and at 57 seconds we have contact. The astronaut announces engine stop at around 60 seconds and we see that dust is still ejected at 66 seconds. Here is a picture from Apollo 14. No clear blast crater can be seen. Here's a drawing of the lunar module. The part shaded in gray is the ascent stage containing the crew habitacle. The lower part is the descent engine used to land on the moon. The ascent engine separates at the end of the lunar stay. Here are some dimensions in imperial units. The lunar module is about 22 feet high, That's 6.6 meters. The descent propulsion engine nozzle is 1 feet and 6 inches, or 47 centimeters above ground. The nozzle has a diameter of 1.38 meters. In the combustion chamber, nitrogen tetroxide oxidizes aerosine 50, producing hot reaction products under high pressure which are expelled at high speed, providing an upwards reaction force that must compensate the gravitational pull for a soft landing. The lunar module had initial masses around 40,600 kilograms, including crew and fuel. On touchdown, about 5% descent fuel remains. The lunar module has then a total mass near 6,800 kilograms, giving a gravitational pull of 11,000 Newton. To counter that 11 kilonewton pull, the combustion products are expelled at 3,225 meters per second. That's near 12,000 kilometers per hour, or over 7,000 miles per hour. Each second, 3.41 kilogram of hot gases are expelled. The product of these gives the 11 kilonewton upwards push. This thrust is the throttle down thrust using during the final seconds of landing. The power of the engine during this phase is 17.7 megawatts. That's the kinetic energy of the expelled gases per unit time. 17.7 megawatts is a large number that equals 23,726 horsepower. This high-speed stream of hot gases hits the lunar surface. To estimate the area directly hit, we need to guess the divergence of the exhaust plume. In the lunar near vacuum, air does not slow down the plume. From the shape of the nozzle, we guess a divergence angle between 5 and 10 degrees, which will be valid for about a few meters. This would give an imprint of 3 square meters when the module is 5 meters above ground and 1.75 square meters when it sits on the surface. Under these conditions, those 17.7 megawatts of kinetic energy would yield a kinetic power density of 6 to 10 megawatts per square meter. This computation emphasizes the dynamic nature of the phenomenon. But understandingly, debunkers prefer a less impressive static pressure number obtained by dividing the thrust by the impinged area, giving values of 2 to 6.2 kilopascal. Are those 6 kilopascal and 10 megawatt per square meter figures significant? Here is a picture from the NASA Phoenix lander on the Martian surface. The Martian surface is covered with a few inches of dust, just like the Moon. You can see that the areas under the landing engines have been cleared of dust, uncovering ice. From the size of the pads, we estimate that these cleared areas have a diameter of 60 centimeters. At 110 newtons per engine during descent, the area should have experienced pressures on the order of 385 pascal. Compare this with the 2 to 6 kilopascal of Apollo. With apologies to any geologists who might be watching, I'll describe the lunar surface as consisting of hard bedrock covered by a few meters of soil-like regolith covered by a few centimeters of fine dust. Fine dust, which is sometimes also called regolith. While being fond of hand-waving himself, Mr. Clavius apparently wants some hard figures, so here's a paper written by one Gromov entitled Physical and Mechanical Properties of Lunar Soil. If we are to believe this paper, lunar soil is homogeneous to a depth of 10 centimeters. In other words, we can expect a layer of 10 centimeters of dust. But then, how does that layer react under various values of pressure? Apparently, the top 15 centimeters can be expected to lose their cohesion above pressures of 500 to 1000 pascals. As the engine was cut off after landing, the area under the rocket was subjected to about 6.2 kilopascal during a few seconds, well above the 1000 pascal cohesion threshold.